What makes working with matrices interesting for this course is that you can partition matrices in multiple ways, and that then leads to different algorithms. So what you've already looked at is what happens if you partition matrix B by columns. Okay, now once you cut B by columns, we found out we also had to cut C by columns, but we could leave A alone. Let's see what happens if we cut A by rows. Alright, so let's cut A by rows. So let's think for a second about matrix C. We know it's going to be a 3 by 2 matrix. Let's again focus on this entry right here that we focused on when we talked about computing C by columns. And let's think, what goes into computing that? Well, it's this row of A inner product with that column of B added to that element of C, right? If you then were to also compute that element, that other element in the same row, then what would happen there? It would be the dot product, the inner product of that same row with the first column added to that element of C. Well, if you took our first Massive Open Online course, you would have learned that this is the same as taking that row and multiplying it times the matrix B. Okay, so we can think of this row is computed by computing the product of the corresponding row of A with the entire matrix B, adding the result then to the row of C. Okay, so how can we say that more generally? We can say, well, what happens if we take our matrix A and partition it into rows? Let's see, there are n minus 1 of those. Oh, wait a second. We decided to use lowercase letters a for vectors. This would be like a whole bunch of vectors on top of each other. That's not the same as a whole bunch of row vectors on top of each other. So to denote that these are row vectors, I'm going to add a T to this label for the row here. Okay? We leave matrix B alone. We notice that C should also be partitioned by rows, so we get C0, C1 through Cn minus 1, like that. Now we might get confused between C0 being a column of A versus being a row of A. So let's actually put something on top of that. We shouldn't put a hat on it because hat we used for original contents. So let's put a tilde on top of this to indicate that these are different labels than the labels we used for the columns. Okay? And then of course we need to add that to those same rows over here. And since we did that, we should probably go ahead and put tildes on A's too, because later we're going to see that we're going to partition A by columns as well. So the confusion wouldn't happen right now, but the confusion will happen later on. Okay, so this is now how we compute. And what we just reasoned is that a typical row in C is computed as the corresponding row of A times the matrix B added to that row of C. And from that we conclude that C, we use I for the row index, tilde transpose, that's just the label for the ith row in C, should be computed as the corresponding row in A times B plus that row in C. So what you can do now is go back and say, how did we come up with a partitioned matrix expression when we had had our discussion about how to compute columns of C from columns of B. Okay, what we did is we took what we learned and we made it into a partition matrix expression. What I want you to do now is to say, oh, we have figured out how to compute if we think of these as individual rows. Let's translate that now into a partition matrix expression so that you discover the partition matrix expression. So why don't you go ahead and do that, and then we'll meet in the next video.